principle. Before the Bernoulli's principle, the third topic, Bernoulli principle is basically hydrodynamics. So what will be the difference between hydrostatics and hydrodynamics? What is the main difference?
Motion.
Now the fluid is moving. So the fluid is moving. Examples where the fluid is moving, many. When you go to the water fountain to drink water, the fluid is moving from the ground to the top and goes at a certain speed. When you have a hose, the fluid is moving, right? So the pump exerts a certain pressure and the water will go out or exit from the hose. And many examples when a plane is moving in air, is moving also, so hydrodynamics. Let's assume for this part of the topic, I will assume that all systems or all fluids have a uniform density. So I won't touch the viscosity here of the fluid, just equal density. In that case, let's say the first thing we will study is the equation of continuity. Equation of continuity is very simple equation that relate. So when we have a pipe of cross-sectional area, I will call A1, and then the fluid is moving to another cross-sectional area that is a smaller cross-sectional area. I will call this A2. Example, the hose have a cross-sectional area, and at the end you have a small exit, and there is a relationship between the velocity, the pressure, and the velocity on this section and this section. Where do you think that the velocity will be greater? In A2. This is basically what is the relationship between cross-sectional area and velocity is given by the equation of continuity. So everybody knows that if you get an atomizer, like perfume bottle, has a pipe inside and then a small exit. When you press, the fluid is coming out at a greater velocity. This is the equation of continuity, basically the principle. So how can we prove that principle? Let's say that we get an infinitesimal element here, which I will call DL1, very small element. And over that, pass a certain amount of fluid, which I will call dm1. The same fluid will go out of here, which I will call infinitesimal length, dl2, and infinitesimal mass, dm2. The mass rate has to be the same. So d, the mass that passed here through a certain time, have to be the same than the mass rate at the second element. But for the fluid, we don't talk in terms of mass. We talk in terms of what? Volume and density. So if it's a fluid and we put rho of the fluid times the volume over dt, that will be equal to rho dv2 over dt, because rho is the same, cancels out. And this is what we call flow rate. This is mass rate. This is a flow rate. So the flow rate is constant over different cross-sectional area. And knowing that, because the flow rate is the same, so if I take that the flow rate here is the area 1, times dl1, so this volume here in this infinitesimal cylinder or area, A1 dl1 over dt will be equal to A2 dl2 over dt. And this is what we call flow rate. So the flow rate will be this times this, which is constant. But what is the derivative of length or distance over time? Velocity. So we get that the flow rate, which is constant, is equal to A1 times what? V1, the velocity on that cross-sectional area. Equal to what? And this is the equation of continuity. This is the equation of continuity, which I said, if the area is bigger to be constant, if this is constant, if the area is bigger, what will happen to the velocity? The velocity has to be smaller. So if this increase, this decrease. If this decrease, this has to increase. And this is the equation of continuity. So when you will use equation of continuity, every time you have two cross-sectional area to find what will be the relationship between velocity and cross-sectional area, equation of continuity. The second topic is the Bernoulli's principle. And what is the Bernoulli's principle? So basically here, when we have two cross-sectional area, you will use the equation of continuity to find the velocity, if you need the velocity. Of course, the area has to be given, and one of the velocity has to be given. Example. Before I go to the Bernoulli's principle, let's go over an example here. Number 16. In chapter 14. Number 16 said, water is flowing at 4 meters per second in a circular pipe. If the diameter of the pipe decreased to 1/2 its former value, what is the velocity of the water downstream? So, the diameter decreased to 1/2 is a circular pipe. If we use the equation of continuity, what can we say? V1 is how much? 4. It's a circular pipe, so we can find the area. The area, 1, what will be? Pi r squared. So will be pi. Let's label R1 square. What will be A2? Pi. And instead of R1, what will be in terms of R2 in terms of R1? What will be? R1 over 2 and everything squared. So will be R1 over 2.